So this is our next application of Biot-Savart's law. Here we are going to derive the expression for magnetic field due to a solenoid. So first is like, what is solenoid? So solenoid is a long cylindrical helical structure. Okay, so it's like a structure like a spring. Okay, and it's like winding closely, but they are not connected. Okay, so they are insulated wires. So it is a large number of tons of insulated wires over a tube. Okay, so there is some base just to make the core. Okay, that can be a cardboard, and that is just some insulator. And then now when electric current passes through this solenoid, then there is a magnetic field which is produced around the solenoid and within the solenoid. So we are going to find an expression for the within the solenoid, how much is the magnetic field. So let us take a finite solenoid. So I just made a cylinder. So this is a solenoid, and this is out of the plane. So current is coming from here and entering here. So it is like this. Okay, so this is the solenoid, and now solenoid is having a radius r and then the length. Okay, so I am going to find the magnetic field at point P. This point P lies somewhere, not exactly in the middle, but this side the length is L2 and this side the total length is L1. Okay, now I am saying that first we go at a distance x, okay, and then take a width of dx. This width of dx, if you look in 2D, it will be rectangle. If you think in 3D, it's basically some turns are coming in with that width dx. Okay, so we are saying that current is I in the coil, and now how much is the total current? Now if you see this dx, what is that dx? Dx is a basically just a, you can say some turns are there in that small width, and current is also flowing. So I current is flowing, and there are, let's say, n number of turns. So total magnetic field due to this current carrying coil can be written at point P. So I am writing that magnetic field dB just due to this ring or coil can be written using the formula for the ring. So what was the formula for the ring? It was mu naught I r square. R was the radius of the ring. So radius of that coil or ring is same as r. So small r square divide by 2. Then on the axis of the ring, the distance is x. So r square plus x square raised to power 3 by 2. Now what is the current? This is the current I only. And if there are n turns, then we have to do times number of turns. How many turns are there? So let us define a parameter small n, and that is number of turns per unit length. So this solenoid is having small n number of turns per unit length. How many turns will be there in dx length, right? Dx is the width. So we'll say that it is basically number of turns per unit length into required length, that is dx. So this is my small magnetic field just produced due to this dx. There are bunch of coils. Okay, so I clubbed all of them and they are kept at x distance. Okay, so we are finding magnetic field due to this coil at x distance on the axis. So I use this formula, right? And times number of turns. There are n dx number of turns in that bunch. So this is my dB, and now I just need to integrate it. If I want to get the total magnetic field at this point, I will simply integrate all such coils. So I will say my x varies from where to where? Minus L1 to positive L2. But we are going to change. So we are not keeping x in terms of L1 and L2. Here, what I am going to do is, I have to integrate this thing, and x is the variable. So I am writing that my total magnetic field is nothing but integration. So just take common constant things out. So mu naught is constant, I is constant, r is radius, right? That is also constant whether this coil is here or anywhere, right? So r is the radius of the solenoid, that's a constant, divide by 2, that is also a constant, and the n is also a constant. What we are left with integration dx upon r square plus x square raised to power 3 by 2. Now for such integration we insert x is equal to r tan theta, right? So I am going to use substitution for this part. So for that I am substituting r is equal to dx sin theta. So my coil, my x was somewhere over here. This my dx, this was my coil. So I am saying that connect it to point P, and let us say this angle is theta. If this is theta, then this is also theta. This is my x, this is my r, and this is right angle. So I'll say tan theta tan theta is nothing but opposite, which is x by r. And that way I can say that x is nothing but r tan theta. Just differentiate this expression, so we get something for dx also. The differentiation of x is like dx, the r is a constant, and tan theta differentiation is sec square theta d theta. And now substitute that in our expression. Our expression was what? Integration of dx over r square plus x square raised to power 3 by 2. This was our expression, right? I'm removing those constant. I'll be back on that page. So I'll be saying dx is what? R sec square theta d theta. That's what your dx. Upon r square plus x square, it will become r square plus r square tan square theta. Like this is x square, so r square tan square theta. You can simply take r square common and you will be left with 1 plus tan square theta, which is what? Again r square sec square theta and raised to power how much? 3 by 2. So by 2 will cancel these two power and eventually we'll get r cube sec cube theta, this entire thing. So this entire thing is r cube sec cube theta. And integration of that, here the sec square can be cancelled from the cube, only sec theta is left, r can be cancelled, so 1 by r square is left. So I'll be saying 1 by r square. Then this is what? 1 upon sec theta, which is nothing but cos theta. So cos theta d theta. And integration of that. Now limit is on theta. So theta is changing from where to where? If you see this figure, from here it was theta that way, right? So I'll be saying we are starting all this way up to here. So theta is changing from, see again, theta is like the direction matters. So theta is that way, means if we are going opposite way, then it is minus theta 1. So it is changing from minus theta 1 to all the way up to 0 and then plus theta 2. So it is this. And when you integrate this, it is nothing but integration of cos theta is sin theta. So I am putting the limit. So I'll get 1 by r square sin theta 2 minus sine of minus theta 1, which will give me minus sine theta 1, and eventually this minus make it positive. So this is the integration of that part, 1 by r square sine theta 1 plus sine theta 2. Now let's move back to our old expression. So this expression was this integration. So I'll be saying it is mu naught how much it is? It is mu naught I r square n over 2. And integration of this thing we already did. It was 1 by r square, in bracket it was sine theta 1 plus sine theta 2. That gives me what? R square gets cancelled and we get mu naught n I by 2 sine theta 1 plus sine theta 2. So that's our expression for the magnetic field due to a solenoid. Again, mu naught ni by 2 sine theta 1 plus sine theta 2. Let's just have a look at the parameter. Mu naught is a constant, 4 pi into 10 raised to power minus 7. N is the number of turns per unit length. Okay, number of turns per unit length for a solenoid, not the total number of turns. And I is the current which is passing in the solenoid. 2 is 2, and then sine theta 1 plus sine theta 2. What is theta 1 and theta 2? If you want to get at this point, then just join this point to this, both ends, and draw a perpendicular. One angle is theta 1, other angle is theta 2. That's what your theta 1 and theta 2 are. So this was a finite solenoid which was having a limited length. If length is limited, both the angles will be limited. But let us discuss some special cases. And before we do that, direction. What about the direction? See, due to that single coil, the direction was what? See, it is coming out of the plane, so going like this. So direction is towards right. Now that coil is over here or over here, the direction is always towards right. So direction on the solenoid is along the axis. Okay, along the axis it is that way. Again, turn your fingers around any one of the loop and then you will see direction is towards the right. So that's how you find the direction. And now we are discussing that some of the points. First is ideal solenoid. What is ideal solenoid? Ideal solenoid is the solenoid which is having infinite length. Okay, so either infinite length or the other condition is the radius of the solenoid. This radius has to be way smaller when compared to length. Okay, so we'll say it will simply become mu naught n I. So how? So formula was mu naught Ni by 2 sine theta 1 plus sine theta 2. So see, if the solenoid is having infinite length, this was our solenoid, and let's say it is having infinite length. So if this is any point P, then I am simply drawing this perpendicular, I am joining it to the other end, and the other end is going towards infinity. So this angle will be 90 degree. Similarly, this also going towards infinity, so this angle is also going to be 90 degree. So theta 1 and theta 2 both are 90 degree, and sine 90 plus sine 90 is 1 plus 1 2. So I am simply cancelling it out, and we get mu naught Ni. So this is an important expression which you should remember. And why it is important? Because whether you take this position or this position, since it is infinite, so at everywhere on the axis, everywhere at this point, this point, this point, everywhere on the axis, the magnitude of the magnetic field is mu naught Ni, and direction is basically as per the turns, it is towards right or left. So it is same everywhere. It is a uniform magnetic field. So magnetic field produced by infinite long solenoid on its axis is uniform. Next is semi-infinite. So if it is a semi-infinite, then basically one angle is going to be 0 and other angle is going to be 90 degree. See, one side it is infinite, other side it is just ending, so other angle is going to be 0. So this sine pi by 2 is 1, so we get only half of the mu naught Ni, or mu naught Ni by 2. So that's the magnetic field at each end of a infinite long solenoid, or semi-infinite means it is still infinite, it just we are looking at one of the ends. So if they are saying that it is infinitely long, what is the magnetic field at the corner? So we'll say it is mu naught Ni by 2.